The following video is of a tensile test. The samples we will be testing are mild steel and aluminium round bar. The machine we will be using to carry out the tensile test is called a universal testing machine. The tensile tester will slowly separate the tensile clamps at a constant speed, applying an ever-increasing load, and will plot this against the change in length of the sample. The graph produced by the universal testing machine is typically known as a stress-strain curve. This curve provides design engineers with a long list of important parameters needed for application design, failure analysis, and quality control. A stress-strain graph gives us many mechanical properties such as strength, toughness, elasticity, yield point, resilience, elongation during load, and the modulus of elasticity. The reason we are carrying out this tensile test today is to determine the maximum load the material can withstand, the percentage reduction in cross-sectional area, and the failure type. A ductile material will show significant necking and a reduction in cross-sectional area, while a brittle material will break with very little plastic deformation perpendicular to the applied load. Typically, as per the Australian standard AS 1391, the test piece must conform to the standard, but generally either a round or square or rectangular in section. The first material to be tested is mild steel. We must measure the samples prior to testing to determine their diameter. This is done so that we can calculate the original cross-sectional area. Using the equation pi d squared over 4, we can take the diameter and work out the original area, which is 31.17 millimeters squared. We will now load the mild steel sample into the universal testing machine. The sample is held by wedge grips that are self-aligning. This type of clamp is ideal when high clamping forces are needed. In this test, we will not attach an X-tensometer. Once the wedge grips are firmly tightened, I will close the safety door and begin the tensile test. This is the digital display of the universal testing machine. The vertical axis is the load in newtons. The horizontal axis is the extension of the sample in millimeters. Eventually, the specimen will begin to plastically deform. Changes in the stress-strain curve will begin to appear during this phase. Once the specimen breaks, the tensile testing is finished. The mild steel sample is now broken. It can now be removed from the machine. You can clearly see the reduction in the cross-sectional area at the site where the fracture has occurred. The broken specimen will now be compared to the undamaged sample by measuring the diameter of the plastically deformed necked section. It measures at 4.2 millimeters. We can now calculate the reduction in cross-sectional area as a percentage. These are the test results for the mild steel tensile test. The maximum load that the sample could withstand was 20.57 kilonewtons. The ultimate tensile strength of the material was 660 MPa. Earlier on, we worked out the original cross-sectional area and the final cross-sectional area. If we take the difference of those two numbers and divide it by the original cross-sectional area, we get the change in cross-section as a percentage, which is equal to 55.56%. So it's quite a ductile material. We will now carry out the aluminium tensile test. Like with the mild steel sample, the first step is to measure the diameter of the sample. So the aluminium sample, its outside diameter measures at 4.8 millimeters. So using the equation pi d squared over 4, we can work out the original cross-sectional area, which is 18.1 millimeters squared. With the sample secured, we will now start the tensile test on the aluminium sample. The material has reached its maximum load-bearing capacity and it will break shortly. The aluminium sample is now broken. We'll briefly inspect the break point and then we'll remove it from the clamps. As you can see, there's significant necking and plastic deformation in the sample. The diameter measures at 3.5 millimeters at the neck section. The maximum load that the aluminium tensile sample could withstand was 3.65 kilonewtons. The ultimate tensile strength was 202 MPa. If we take the difference between the original cross-sectional area and the final cross-sectional area, and then divide that number by the original cross-sectional area, we'll get the change in the cross-section as a percentage, and it's 46.83%. The fracture type of both materials is ductile, with the mild steel sample having a cup cone type fracture. These are our final results for the mild steel and the aluminium tensile samples. So the mild steel sample was able to withstand a maximum load of 20.57 kilonewtons. It had a reduction in the cross-sectional area of 55.56%, and the failure type was a cup cone ductile fracture. The aluminium sample, it was able to withstand a maximum load of 3.65 kilonewtons. It had a reduction in area of 46.83%, and the failure type was also a ductile fracture.